This is Mike Johnson with AMRI. AMRI provides instruction in the world of machine lubrication, leading towards learning best practices. We often get questions during our classes related to lubricant selection. Here's one that came up in a recent class. How does the bearing bore size impact grease selection? Well, let's take a look at that. We should probably start with defining what kind of bearing we're talking about. There are element bearings, like we see in this graphic from ATS Electrolube, that come with a variety of element shapes, sizes, and names. The element is the piece between the two rings. We have cylindrical rollers, tapered rollers, spherical rollers, all kinds of element shapes. That fundamentally defines how often we're going to lubricate, but not necessarily what lubricant's the best fit. In order to determine which lubricant to use, whether oil or grease, we need to understand the bearing's parts and understand how those parts influence this decision. So let's define the parts first. Bearing manufacturer textbook or handbook will identify the point between the 12 o'clock position to the 6 o'clock position on the outer ring outside of the bearing as the outside diameter, or OD. The manufacturer will refer to the gap between the 12 o'clock and 6 o'clock position inside the inner ring as the bore, or the ID. The axial face plane from one side to the other side of the bearing is referred to as the width. All these dimensions are generally considered in millimeters, and they all come to play in determining which product is going to be used. The remaining variable, which is a very, very important variable, of course, is the speed with which the shaft is turning. The speed is referred to with a small n value in almost all of our machine maintenance reliability calculations. At this point, I'd like to introduce you to the beginning of a handful of a few universal lubricant selection rules. Rule number one. The lubricant selected must contain oil, whether it's oil or grease product that you're looking at, where that oil moves proportionally to the speed that the machine parts move. The machine that has fast-moving parts must have fast-moving oil. The machine that has slow-moving parts must have slow-moving oil. So when making this product selection decision, our first chore is determine whether or not this bearing is moving at a speed where grease can be an acceptable option. The bearing manufacturers give us a target range, a speed limit value, if you will, for the use of grease. The bearing manufacturers would have us to calculate the NDM value, N shaft speed times DM bearing median diameter. DM is ID plus OD divided by 2. So we calculate this value, and it gives us an idea of what the angular velocity characteristic is for this bearing, and then from there we can compare to some standardized unit values to determine whether grease is a good fit. Once we've calculated the NDM value, we want to compare the value we get to a set of tables provided by the bearing manufacturers, where we can find whether grease is going to be a good fit, according to the bearing manufacturer, for 4 different types of bearings that differ based upon the shape of the element and the amount of axial loading. The more element to race contact and the greater the axial loading characteristic based on bearing design, the less effective grease is going to be. We need to determine whether it's safe to lubricate with grease before we go to the next step. So we calculate NDM. We compare to our chart here of established values, and we know which way we need to lean. The next step, once we determine whether it's grease or oil, will be to identify the viscosity that's required at operating temperature in order to make the elements in the rotating shaft float in the race. We can do this one of 2 ways. We can either plot decisions on a chart provided by the bearing manufacturer's lubrication handbook, or we can calculate the values. For our part, we would rather calculate so that we know exactly what it is we're talking about and what it is we have to have. The calculation is the minimum allowable viscosity equals a constant factor, 27,878, times variable shaft speed to the negative 0.7114 power times the bearing's median diameter to the negative 0.52 power. This can be easily done using Excel or a calculator. And then once we have the minimum allowable viscosity identified, we're going to multiply that lowest allowable viscosity limit times 3 to come up with our target viscosity value. Since most of us are not all warm and fuzzy with Excel and or calculators, there's an alternative way to determine the minimum allowable viscosity to a satisfactory extent. Back to our median diameter calculation, ID plus OD divided by 2 gives us DM value. If we have the DM value, find the bearing manufacturer's lubrication catalog, find the chart that has the bearing mean diameter on the bottom axis and the viscosity grades on the diagonal vertical axes, we can find the median diameter and the relative shaft speed. Let's say in this example is 1200 RPM. 150 millimeter bore dimension at 1200 RPM gives us a drop dead viscosity value of 12 centistoke. We multiply that by 3, and now we have a target of 36 centistoke viscosity at operating temperature. That is a great fit for this bearing. The last step in our exercise is to validate that the product that we have in mind for this bearing application is going to be a good fit. This is a fairly simple process, and we've already identified that we have a target viscosity of 36 centistoke. Drop dead was 12. 12 times 3 is 36. We really like to end up in the 3 to 5 times value when we're making this pick, so we have a little bit of room for temperature excursion for the operating bearing. So then, now we're going to go out and measure the temperature of the bearing. And let's say hypothetically we come up with 122 degrees Fahrenheit or 50 degrees C. We think that we want to use a electric motor grease. And we look up the viscometric properties of the electric motor grease, and we find that it is a viscosity grade of 100. So we identify the vertical or diagonal viscosity line 100. We plot the temperature at 50 degrees C on the chart, moving from left to right. Where we bump into the diagonal 100 viscosity line, we drop straight down, and that tells us what our working viscosity is at that 50 degrees C temperature. So now we see that we are at 5 times the drop dead viscosity. 12 was our drop dead point. We had to be above that. We say we want to be between 3 to 5 times the drop dead point to give us a little bit of excursion room. We're setting right at 5 times the drop dead viscosity. In this instance, we would say, okay, that's a good pick. It's time for us to make this decision and then go find another problem to solve. Thank you for your interest in this topic. If you'd like to know more about machine lubrication and oil analysis, or you have an interest in certification coursework, please reach out to us at amory.com. This is Mike Johnson. I can be reached at mike.johnson@amory.com or info@amory.com.